Okay, hi there. So today we're working with 8.7 Taylor-Maclaurin series. And whether it's this book or not, 8.7 Taylor-Maclaurin series is a staple for BC Calculus. So we want to find the polynomial approximations of elementary functions and compare them with the elementary functions. And we want to use a graphing calculator at times. We want to find Taylor and Maclaurin polynomial approximations of elementary functions, and then we want to use the remainder of a Taylor polynomial to be able to determine what is the error, how far away are we, or what are we comfortable with in terms of error availability or acceptability. So polynomial approximations of elementary functions, we've used Euler's method before to approximate a function, and we're looking at developing functions that resemble a function in terms of their value, their shape, their slope, their concavity. So we want to see approximations, and we can use Taylor-Maclaurin series to do that. And sometimes we have a radius of convergence. In this first example, we're looking at a graph and we say consider any function f of x, knowing that p of c is approximately f of c. Around that yellow neighborhood that you see p is a linear polynomial and f is a curve. So the line doesn't really get too close except right at c. But if we increase the number of terms of a Taylor polynomial, we can then get really close to what the function looks like around that C point. So for the first example, to find a first degree polynomial approximation for the function f of x is equal to e to the x, find a first degree polynomial function p with a one there means the first degree is equal to a sub 0 plus a sub 1x. It's just like an mx plus b formula. So the first step is going to be, I want the function to have the same function value as e to the x at 0. So I'm going to say f of x is e to the x, so f of 0 is 1. So f prime of x is the slope, and that's also e to the x. So we want f prime of 0 to also be equal to 1. So you can see in step 2, we take the function, and remember, we want this function to pass through 0, 1. So we take our form for the linear function, a sub 0 plus a sub 1x, and we say p of 0 is going to equal a sub 0. And since p of 0 is equal to, we want it to equal f of 0, we want it to equal 1, then that means that a sub 0 must be equal to 1. Then in step 3, we're going to plug in our 1. So p of x, now a sub 0 plus a sub 1x, is now equal to 1 plus a sub 1x here. Then that means p sub 1, the p prime of p sub 1 of x is a sub 1. That would be the slope of the ax term. So we know p prime of 0 is equal to f prime of 0 is equal to 1 then. A sub 1 must be 1. So then putting that all together in step 4, we have our linear approximation for the curve, and we've kind of done things like this before, it's just set up in a different way. So we get our first degree polynomial to approximate e to the x is 1 plus x. So then we have polynomial expansions of functions where we'd start off and we'd say, okay, if we're going to center our polynomial at c, it would look like this following, our nth degree polynomial. So where we have a constant, plus we have a constant times a minus c to the first power, plus another constant a sub 2 times the quantity a minus c to the second power, that's our second degree term, a sub 3, and so on all the way up to a sub n times the quantity x minus c to the nth power. So this is our polynomial expansion centered at c. So now if I take the derivative of that, p prime of the nth degree polynomial, you can see I get this next line. So with the next line, you see that the derivative of the first term is 0, so that drops out, and the derivative of the second term is just a sub 1 times 1. And then you can see as you go down, you're using chain rule, right, or the generalized power rule, and so you get the following, p prime. Continuing to do that, you get p double prime. Remember, a's are constants. And then you start looking at this last term, and you start to see that n times n minus 1, and then p triple prime, you end up with the 6 a sub 3 And we're leaving some things out here, but you see this idea n times n minus 1 times n minus 2. And you start thinking in terms of factorials, right? So eventually, the nth degree, the nth derivative of the nth degree polynomial would look like this, okay? Where it would finally just take the derivative of just the last term, and you would have all the factorials n factorial times a sub n. So now, if we let x equal c in all of these, you can see that p of c would be equal to a sub 0, right? All the other terms would drop out except for the constants. P prime of c, a sub 1, you can look above. P double prime of c is 2a sub 2. P triple prime is c 6a sub 3, and so on. Okay, so for Taylor polynomials, you can see that what we want is we want f of c. I'm going to zoom in on this. F of c, we want it to be equal to, we want the graphs to have the same shape. So if we have a graph that goes something like this, right? We can kind of picture our graph, like say this is our c value right here. We want, and we might have a situation like this where the function might wrap around and then it diverges at a certain point. And then maybe we can get the next iteration, maybe go a little bit further. Maybe we have a higher degree. Maybe even goes like this, right? Or something like that. Maybe at the ends, maybe goes up a little differently. Maybe it goes like this and like this and like that. So depending on the degree, it could be odd. Anyhow, so what we want to do is we want to have it start to wrap really close to the function. Now, for me, the function is blue there. So you can kind of see as we have our function, we want our function to equal our polynomial in terms of the function value and the derivatives. So it produces the same shape around our center, C. So this is the way our polynomial starts to look, because we have our derivatives, right? So we have f of c, okay, our p, our first degree, a sub 0, is just going to be f of c. Then we have our a sub 1 is going to be f prime of c, right? And then there's your times your x minus c in your Taylor expansion. And then f of f double prime of c is equal to 2 a sub 2. So we're going to replace a sub 2. We're going to replace a sub 2 with f double prime of c, but we have to divide by 2 and then multiply times your x minus c, the quantity squared, okay? And then we continue. You can see where we're starting to develop a pattern here where we have f triple prime of c. And if I do the division here, we're going to get f triple prime of c over 6, which is 2 times 3. A sub 3 is equal to that. And so then we multiply by x minus c cubed then. And then after that, then we have the fourth derivative centered at c, fourth derivative evaluated at c over 4 factorial, which is 2 times 3 times 4. And the pattern just continues, x minus c to the 4th power. And then we would just continue where we're adding ... till we get the nth derivative of c over n factorial times the quantity x minus c to the nth power. So that is your Taylor polynomial form, right? And for the next couple of examples, we're looking at some numerical values, so you can get them with a calculator, and I urge you to try these values out with your calculator. So what we're going to do is we're going to use the third degree polynomial. We're going to construct a table comparing the values of the third degree Maclaurin polynomial, which is a Taylor polynomial that's centered at 0, with the suggestion that f of x is equal to e to the x for several values of x near 0. So using the calculator and comparing the value of the third degree polynomial, you can see that they're pretty close and you have some convergence. If you look, when you're at -1, now remember the center is near 0, so it converges exactly at 0. But you can kind of see as you move out, you lose that convergence where you're at 0.1 away, you have a tenth, you have a hundredth and thousandths that it converges to, actually 10,000ths. And as you move to the left, you have 0.90483. So again, the same thing, 10,000ths here. Actually, 100,000ths. So, right, thousands, 10,000ths, and 100,000ths there. So you have convergence of those decimals. And then as you're at negative 0.2, you have 818, and you lose the convergence of the decimal places. And further away at negative 1, you can see you've only got a tenth convergence. So you have 1.22, 221. Here at 0.2, 1.221. And then at 1, you lose that convergence. Here you have a 2.71, and here you have a 2.66. So as you get further away from the center of your Taylor polynomial, then you lose the accuracy for the approximation. So you can use a table and then use table set to get these values pretty quickly and make your delta t equal to 0.1. Okay, and you can put the y1, if you're not familiar with this, put the y1, make it e to the x, and y2, you can make that your Taylor polynomial of third degree. Okay, and then the same thing here when you're checking this out, finding the nth Maclaurin polynomial for f of x is equal to the e to the x. Check this out with your calculator, and using alpha trace, I think it's a little bit easier to get the equations in there, because you can type in your y sub 1, and that's pretty easy to type. Once you do y sub 1 is equal to 1 plus x, then what you can do is you can type in y sub 2 for your second degree Taylor polynomial. You can type in y sub 1 and then just type in plus x squared over 2 factorial. And the same thing as you keep going up, y sub 3. So I'm doing y sub 1 is the first degree, y sub 2 is the second degree, y sub 3 is the third degree Taylor polynomial. And so you can just type in y sub 1, or you won't be typing that. You'll be using your alpha trace for that to pull up the y's, y sub 1 plus, then you have x cubed over 3 factorial. So, oh, I'm sorry, y sub 2 for y sub 3. So you keep adding the previous one. And so as you're building this, you can kind of see here's the formula I'm using to do this. But just check these out. You can turn off your previous, you can turn off e to the x if you want to, or you can leave e to the x on and turn these off if you hit the enter over the equal sign in your calculator. So make sure your y sub 1, 2, 3, 4, 5, however many you put in, make sure that they are different colors, and you can kind of see where the convergence occurs, and also get a good window in there so it's not looking too small. Okay, right now I'm going to start with, or leave off here, and I'll send you a part 2 video for 8.7 Taylor and Maclaurin series. I'll see you when I see you. Alan out.